Section 14.7 is triple integrals in cylindrical and spherical coordinates. So remember, way back a few chapters ago, we talked about cylindrical and spherical coordinates, and then we just sort of left it at that. This is all going to come back in this section. So if you need to pull out your formula sheet to remind yourself of those conversions. Let's start with cylindrical. So recall cylindrical looks like polar coordinates in the xy plane. So x is r cosine theta, y is r sine theta, and then z is just z. And so we're going to think about a standard cylindrical block as, oops, so x, y, z here. Think about taking, say, a polar sector and then raising it up in the z-axis. Sorry. Oh boy. Okay, we've all established that my artistic skills are lacking. I'm gonna make my sector a little bit bigger. Let's do something like this. Okay, something like this, and I've got my little polar slice down here. Okay, so we can think of change in z here, and then down here I've got some delta Ri, change in r, and I've got a change in that arc length, Ri delta theta I. All right, and we can think of the x-axis as where theta is 0, and the y-axis is where theta is pi over 2. Okay, so if we do this, we're going to convert dv into cylindrical coordinates using r dz dr d theta. Notice this is just taking our conversion to polar coordinates and lifting it up into 3 space. So if Q was my solid region defined by the set of points x, y, z with x, y in some region D in the plane, and then z bounded by functions u1 and u2 of x and y, then in cylindrical coordinates, we're going to define Q to be the set of points r theta z, where theta is bound by some angles alpha beta, r is bound by some, h1 of theta, h2 of theta, so some functions of theta, and then z is going to be bound by u1 of r cosine theta, r sine theta, and u2 of r cosine theta, r sine theta. All right, let me turn my page. Well, maybe I can fit it in here actually. So the triple integral over Q of f of xyz dv becomes the triple integral with bounds alpha to beta, h1 of theta to h2 of theta, and this last one is kind of messy, u1 of r cosine theta, r sine theta, oh boy, u2 of r cosine theta, r sine theta, of f of r cosine theta, r sine theta, z, r, dz, dr, oh my goodness, I can't fit it, d theta, squeeze it in, hold on. Okay. All right, so let's actually try to do an example here. So I want to evaluate the triple integral over Q of y dv, where Q is the region below the plane z equals x plus 2, above the xy plane, and between the cylinders x squared plus y squared equals 1 and x squared plus y squared equals 4. All right, so again, a rough sketch of what we've got here. So z equals x plus 2 is gonna cross at -2 on the x-axis, so it's a plane back here that runs parallel to the y-axis, right? I'm just gonna draw this part of it for now. And we have the cylinders x squared plus y squared equals 1, and that's going to be lifting up towards that plane until it crosses that plane. And x squared plus y squared equals 4. Again, this is a rough sketch. Okay, maybe that's helpful, maybe it's not, but this is kind of what we've got going. So at the top, I've got my plane z equals x plus 2, and I'm looking at the region between these two cylinders heading up into hitting that plane. Ugh. Something like that. Okay. So let's think about our slices. This is set up really for cylindrical coordinates, right? Because I've got two circles here in the xy plane that are bounding my region of integration. So let's start with my bounds on z. Well, z is going to go from the xy plane down in here up to this plane z equals x plus 2, but I want to put that in cylindrical coordinates. So it goes from 0 to x plus 2, but x is r cosine theta. So I have r cosine theta plus 2. Now what about r and theta? If I focus in down here, I've got a circle of radius 1 and a circle of radius 2. That's terrible, but let's go with it. And we're looking between those two. So my r goes from 1 along this circle up to 2 along that circle. So my bounds on r, our r goes from 1 to 2. And finally theta, well, I'm going all the way around the circle, so theta goes from 0 to 2 pi. The hardest part of these problems is just getting your integral set up. Okay, now that I've got my bounds, I just plug and chug, okay? So I'm going to look at the integral from 0 to 2 pi of the integral from 1 to 2 of the integral from 0 to r cosine theta plus 2 of y, which is r sine theta, r dz dr d theta. All right, let's do it. I have 0 to 2 pi of the integral from 1 to 2. We want to integrate first with respect to z. There is no z here, so I just multiply by z, so I get r squared sine theta times z, evaluated from 0 to r cosine theta plus 2 dr d theta. It's going to give me the integral from 0 to 2 pi of the integral from 1 to 2 of, can I multiply it out at once? Sure, let's do it. So I'm going to get r squared sine theta times r cosine theta plus 2, all in parentheses. So when I distribute, I get r cubed sine theta cosine theta plus 2 r squared sine theta dr d theta. Okay, so I want to integrate with respect to r. I get 1/4 r to the 4th sine theta cosine theta plus 2/3 r cubed sine theta, evaluated from 1 to 2 d theta. Integral from 0 to 2 pi. Let's clean this up a little bit. I get 1/4 times 2 to the 4th sine theta cosine theta plus 2/3 times 2 cubed sine theta minus 1/4 sine theta cosine theta plus 2/3 sine theta d theta. Let's copy this and turn the page. All right, what do we have here? Integral from 0 to 2 pi of 4 sine theta cosine theta. Well, let's do the subtraction too. So I'm going to get 4 sine theta cosine theta minus 1/4 sine theta cosine theta. So that's 16 over 4 minus 1 over 4, or 15/4 sine theta cosine theta plus, okay, so I get 16/3 minus 2/3 is 14/3 sine theta d theta. Now to integrate here, you can use a u substitution to integrate, or you can use the double angle formula. So recall, sine of 2 theta is equal to 2 cosine theta sine theta. So I have a sine theta cosine theta here. If I divide both sides by 2, 1/2 sine 2 theta is cosine theta sine theta. Can't fit it on there. So I'm going to replace that here. I have the integral from 0 to 2 pi of 15/8 sine of 2 theta plus 14/3 sine of theta d theta. And actually, let me split these integrals. So I'm going to put a d theta in here. Integral from 0 to 2 pi d theta. All right, so for this first one, I need to do a u substitution of 2 theta. I need a 2 out here and a 1/2 out front, right? So the derivative of 2 theta is 2 d theta, so that's in there. The integral of sine of u is negative cosine of u, so I have 15 over 16 times negative cosine of u, which is 2 theta, evaluated from 0 to 2 pi, plus 14/3, the integral of sine theta is negative cosine theta, evaluated from 0 to 2 pi. So that's going to give me 15/16 times negative cosine of 4 pi minus negative cosine of 0 plus 14/3 times negative cosine of 2 pi minus negative cosine of 0. And this is 0, right? Cosine of 4 pi is 1, cosine of 0 is 1. So I have negative 1 plus 1 is 0. Same idea here. So overall I get 0. So all that work and all we get is 0.